All right, how's everybody doing today? Good. Cool. Okay, so today we're going to start with a brief review of series. So last time we talked about series circuits, so we'll remember what series means, why we care about it, and then how we can calculate resistance in a series circuit, find an equivalent resistance. And then we'll remember a little bit about Ohm's law in series, and we'll recall that when you have a series circuit, the current will be constant for all of the components, but the voltage might change from one component to another. Then we'll go on and do our lecture for today, which is about parallel circuits and parallel resistance. So we'll start off by saying what is parallel, and then why do we care about that? And then we'll have a game kind of like we did last time, only this time we'll have to figure out whether a circuit is in parallel or not, okay? And then I'm going to explain a little bit about the general resistance, or the general concept of resistance in a parallel circuit. Now in series, we found out that when you had more resistors, you got more resistance. Kind of makes sense, right? Turns out in parallel, it doesn't work that way. So it's a little bit of a strange thing to wrap your mind around. So I'll talk a little bit about the general concept, and then I will talk about how we can actually do some calculations to figure out real numbers for parallel resistance. So I'll show how we can calculate the equivalent resistance when you have several of the same value of resistor that are all in parallel. And then I'll also show how we can find the resistance of different resistors in parallel. And then we'll switch topics for a minute and we'll talk about calculator practice. So this is how you can use your calculator to do calculations with big or small numbers. So we've already talked about metric prefixes like kilo, mega, giga for large numbers, or micro, milli, nano for small numbers. Well, today we'll talk a little bit about how we can enter those numbers quickly into our calculator and how we can do calculations with those. And then for homework, I'd like you to work on the parallel resistance quiz and also on the calculator practice. Oh, one more thing before we get started. 1 week from today, we're going to be going on a field trip to the old Folsom Powerhouse. Yeah, so that should be super exciting. We've done this many times before, and it's always a fun time. So that'll be.
Is that the first one they built here?
Yes, yeah. It was built back in the 1890s, I think it was completed, something like that. So it's very old. It's antique. It's got this super cool steampunk vibe to it. You know, it's got all these gauges and old-fashioned equipment, and you get to walk right up to it and really see it. And the thing is that the way that power has generated really hasn't changed all that much from the time when this powerhouse was created until now. Basically, the main difference is that now everything is bigger. Okay, but the way that power is created is still the same. What happens is that you get water coming down and pushing turning a giant shaft, and then that turns a generator, and then that creates the electricity. So that's the way it was done then. It's still the way that it's done today. And so when we go and we get to see this place, you really get to be up close and personal and see all this equipment. So it's super cool. There is an announcement that I just posted this morning about that. And on that announcement, there's a map and there's also a liability waiver. So I would like you all to fill out the liability waiver. So this is very similar to the one that you all filled out when the class started, but this is for the field trip specifically. So you need to fill this one out in addition. Even though you've already filled out the one for the class, you also need to fill this one out. So I've created an assignment for that. You just download the waiver, you fill it out, and upload it to the assignment. Okay, so please fill that out. I'll go over the map in class on Tuesday and remind everybody about it. But it shows how to get there, and we all want to meet there at 9:45 in the morning. And yeah, 9:45 next Thursday, a week from today, at the old Folsom Powerhouse.
Is there free parking or you have to pay?
There is free parking. The parking at the powerhouse itself costs like $10. But fortunately, there's a free parking lot about a block away. So that's where I always park. That's where I recommend that you park. That's all shown on the map on the announcement, so you can check that out, and I'll go over that all on Tuesday, okay? But we want to meet there at 9:45, and then our tour starts promptly at 10. So the tour will run from 10 to 11:30, and then after that, you're free to go. This is not required, but it is extra credit. So, and I highly recommend it. It's a great experience. It's a super cool thing. The school does not provide transportation, so it will be up to all of you to get there. You can drive there. You can take public transportation, or you can carpool, however you like. But that's what's going on. Okay, so next Thursday, field trip to the old Folsom Powerhouse. So, questions about that? All right, so then let's get started. So let's review series. So what was the definition of a series circuit?
They don't touch.
Yeah. So the general
There's nothing in between.
the general configuration for a series circuit was in when components are connected end to end, like trains on a train track, right? And we had a more specific definition. We said that for a series circuit, the end of one component is connected to the beginning of the next with nothing in between. So this is kind of the way we think about series circuits usually, but really the shape of the circuit didn't matter as long as it followed this definition. So you could have resistors like this. Would that be in series?
Yeah.
Yeah, because the end of one component is connected to the beginning of the next one with nothing in between. But if we have something like this, but we have another component connected here, then that is not in series because we do have something in between the other two. So this is series. This is not series. Okay? So that's what series meant. Questions about that? Okay. So then we talked about how we could calculate resistance for a series circuit. So what was the formula for resistance for a series circuit?
Just add it all on.
Yeah, you just add all of the resistor values together. So if you have something like this, and you have 200 ohms, and another one that is 300 ohms, that would be equivalent to a single resistor. And what would the value be for that one? Yeah, 500 ohms. Okay? So that's how we calculate resistance in a series circuit. Not much to it. Questions about that? All right. So then we also looked at how we could do calculations for Ohm's law in a series circuit. So so let's say we have a series circuit here, and we've got, say, 10 volts there. And we've got, say, 4 ohms there and 1 ohm there. And we want to find the voltage and the current for these two resistors. Well, the first thing that we can do, we don't really know how to do Ohm's law when we have two separate resistors. So what we can do is we can combine these two resistors and find the equivalent resistance for those two. So what we do is we combine those two. So when you put 4 ohms and 1 ohm together, you just end up with 5 ohms. And you still have 10 volts over here. So now we have a circuit that has a voltage and a resistor, and we want to find the current. Do we know how to do that? Yeah. So we can use Ohm's law to do that. Remember, we write Ohm's law like this. We've got V, I, and R. So we want to figure out the current. So we write down I equals, we cover that up, and we see that it's V over R. So that is 10 volts over 5 ohms. So that comes out to be what? 2 amps, perfect. All right, so we have 2 amps flowing through our circuit here. So that's the amount of current flowing right there. And since these two circuits are equivalent, if we have 2 amps flowing out of the power supply in this circuit, that means we also have 2 amps flowing out of the power supply in that circuit. Okay? And that 2 amps flows around, and how much of it goes through this first resistor?
2 amps.
Exactly. All of it, 2 amps, because it has nowhere else to go. Remember, it's like water flowing through a pipe. We just have one long pipe here, so whatever water is flowing in this part also has to be flowing in this part. And it also has to be flowing in this part down here. So how much current is flowing through this resistor there? 2 amps, perfect.
2 amps.
Yep, and how much flows back into the power supply? 2 amps, exactly. Always, the amount of current flowing into the power supply is always the same as the current flowing out. All right, Perfect. So now we know the current for each of the that's flowing through each of these resistors. So can we figure out the voltage across them?
Yes.
Yeah. And what law do we use for that? Ohm's law. Perfect. So here we want to figure out the voltage. So we write down V equals, we cover that up. We see that it's I times R. So that is, for this first one, what would be the current? Yep, 2 amps. And the resistance? Yeah, the first one is 4 ohms. So, yeah. And so that comes out to be 8 volts. So we have an 8-volt difference across this resistor. We can also figure out the voltage across this resistor down here. So again, we say V equals I times R. What is the current for this resistor? 2 amps. And what is the resistance there? Yeah, 1 ohm for that resistor. So that would be 2 amps times 1 ohm, and that comes out to be 2 volts. So, yeah, so we have a 2-volt difference from one side of that resistor to the other. So, are there questions about that? All right, so that's how we can use Ohm's law to figure out the voltage and current in a series circuit. The general procedure is to find the equivalent resistance and then find the current for the circuit, and then use that current to find the voltage and current for the other resistors in that circuit, for each resistor in that circuit. So, questions about that? Okay, cool. So that was a little bit about Ohm's law in series. And we can see that when we have a series circuit like this, the current is going to be the same for all of the components in that series because they're all, that's basically the definition of series. The end of one component is connected to the beginning of the next. So all the current that flows out of one has to flow into the next one. It has nowhere else to go. So for a series circuit, the current will be the same for all of the components, but the voltage may be different. Could you have a series circuit where the voltage is the same for each component?
Yeah.
Yeah? Yeah, I think you could. So what would you have to do in order for the voltage to be the same? What would the circuit, what would have to be the case in the circuit?
Resistors have the same amount of ohms.
Exactly. If you have a circuit where all of the resistors have the same value, then, and you have the same current flowing through each one, then the voltage across each one will be the same. Remember, voltage is just current times resistance. So if each resistor is the same and all the current is the same, then all the voltages will be the same as well. So it's possible to have the same voltage in a series circuit, but in general, the voltages can be different. Okay? So, any questions about series circuits? Okay, cool. Then let's go on and talk a little bit about parallel circuits. Red marker is powerful, doesn't want to go away. All right. So, in parallel, so the basic definition of parallel is that Um, the beginnings of all components are connected to each other. And the ends of all components are connected to each other. So a simple example would be like this. So all of these components are connected in parallel because the beginnings of all the components are connected to each other and the ends of all the components are connected to each other. Okay, so that's what parallel means. So why do we care? Well, just like with series circuits, we find that if we look in the real world, many real-world circuits are connected in parallel. So we said that old-fashioned holiday lights were connected in series, but there was a problem with that. What was the problem with that?
If you broke the connection, the entire thing failed.
Exactly. So one bulb goes out and the whole string is gone, right? So that was a problem. So modern holiday lights are not like that. With modern holiday lights, if one light goes out, the rest of the string keeps working. And that's because modern holiday lights are connected in parallel. Okay? So that's one example. Another example might be speakers. So if you have a big PA system and you want to play some really loud music, you might have several groups of speakers and you might hook them together so that they're all being run from the same music source. So you might have a music source here, and then the speaker is essentially just a big resistor. So you might have several speakers that are connected together like this. And those would be in parallel because the beginning of one is connected to the beginning of the other and the ends are connected together also. So that would be another example of a parallel circuit. Really, many circuits in the real world are connected in parallel. Oftentimes, when you're designing a circuit, you will have a power source here, and then you'll just have long wires, essentially, that come from this power source, and then you can put the elements that need power and connect one side of the element to the positive side of your power supply and the other part of this element to ground. So you could have, one section in here that has maybe a transistor, and then another section that has, say, an amplifier, and you could have the signal from one going to the next. And basically, each one of these sections draws power from the power side and returns the electricity to ground. And so anytime you need a new section in your circuit that needs power, you just put it in parallel like this, and it draws power and ground from your power supply. And this is the sort of the starting layout of the transmitter and the receiver that we'll be talking about later in the semester when you get to build your own boards. Their circuits are laid out very much like this. They have a power supply and then lots of elements that draw power and ground from that power supply. So in the real world, many things are connected in parallel. So if we can understand how parallel circuits work, that will help us to understand how real circuits work, okay? Or parallel sections of real circuits work. So that's why we care. Any questions about that? All right, so then let's go on and do a quick game, and we'll play Is It in Parallel? Sounds like a game show, right? Now I know how I'm going to make millions of bucks, Fred. Got my camera, I got my game show, I'm all set here. All right.
Are you going to have prime time?
Yeah, right. Yeah, we'll work on that. So, okay. So let's see. So if we have a circuit like that, is that in parallel?
No.
Yeah.
Yes, it is.
Because the beginning of one component is connected to the beginning of the next. The ends are all connected together. So, yep. So that looks good. What if we have a circuit like this? So we've got a wire going from here to there, and then another wire from there to there. This little hoop thing in the middle means that those two wires are not connected to each other there. So is that in parallel?
Yes.
Yeah. Because you can imagine if these were wires and this was, in the real world, you could just kind of flip this resistor around, and then you'd be back to kind of that configuration there. So those two resistors are also in parallel. Okay. What about this?
Series parallel. Series.
Right. So it's not parallel. These two parts are parallel. Well, they kind of look like they're parallel to each other because they're side by side, but it's got this other resistor in between them. And so, yeah, so this is not parallel.
Couldn't you find the equivalent resistance between two of the resistors, and then it would be parallel?
Aha, yeah. So, right, so you could rearrange that, and then you could say that like this section is in parallel with this section. Yeah, and we'll be talking more about that sort of rearranging in a day or two, a couple days. So when we start talking about series and parallel circuits, but altogether, you could not say that all three of these resistors are in parallel. Okay? Let's see, what else? So, all right. Could you say that these resistors are in parallel? Yeah. Yeah, they are, because the beginning of all of the resistors are connected to each other, and the ends of all of the resistors are connected to each other. So even though the resistors are laid out in a line, and that's kind of the way we sort of think about series, these are actually in parallel because they fit that definition. Okay? So really, the shape of the circuit is not the important thing. The important thing is that it fits this definition. So that's what's going on there. So do you have any questions about parallel circuits here? Okay. All right. So that brings us to the end of our parallel game. So let's talk a little bit about resistance in parallel. So we said that when we have resistors in series, the more resistors you have, the more resistance you end up with. Kind of makes sense, right? It's sort of it's sort of logical, intuitive. But with parallel resistance, it's actually the opposite is true. In parallel, the more resistors you have in parallel, the less resistance you have overall. So more resistors equals less resistance in parallel. So more resistors in parallel equals less resistance. So this is a weird concept. It makes sense kind of when you think about it at first blush. But let me try to explain why this is the case. So we said that electricity behaves kind of like water. So imagine you have water flowing through a stream, and then it comes to a narrow section in that stream, and all the water has to flow through that narrow section. That's kind of like electricity flowing through a single resistor here. The resistor is like that narrow part in the stream. But now imagine you got that same stream, you got that same narrow part, but now there's like an earthquake or something, and now all of a sudden another section opens up right next to that first spot. So now the water has another channel that it can flow down. So it can still flow down that first one, but it can also flow down this other path right next to it. And then the two streams meet up later on. Is it going to be easier or harder for that water to flow now? Easier, exactly. It's got two paths that it can travel down, so it's going to be easier for the electricity to move now. So that's what happens when you have parallel resistances, or resistors in parallel. You're giving the electricity more paths that it can take, and so it's easier for it to flow. So, and this brings me to kind of a common misconception about electricity. Has anybody heard the phrase, electricity takes the path of least resistance? Anybody? A couple people? All right. So that's a common phrase, and it's sort of like many things. It has a grain of truth to it, but it's not completely accurate. So you can think about it again like water flowing through a stream. So imagine you have water flowing down, and you got this big river, and then it comes to a fork, and one side of the fork is kind of narrow, and then the other side of the fork is kind of a wide open path. And then later on, these two join up again. This is kind of like electricity having two paths to travel down, one with more resistance and one with less resistance. So if you had a stream like this, most of the water is going to go down the bigger path, right? Because it's got more room for the water to travel. So that's where most of the water is going to go. And the same thing is true in electricity. If you've got two paths and one has less resistance, most of the electricity is going to go down that path. But if you have a stream like this, and you've got a big path on one side and a small path on the other, does that mean that the water is just going to completely avoid the small path because it's easier to travel down the big one? No. Some of the water is still going to go the other way. It's going to be a little bit less than can flow down the big path, just because there's less room over here. But you're still going to have some water flowing down that way. Okay? So it's the same way with parallel circuits. If you have two resistors and one of them has less resistance, it's going to get more current. One has more resistance, it's going to get less current. But you're still going to get electricity flowing down both paths. So that's what goes on there. So when people say electricity takes the path of least resistance, really it divides itself up so that it flows and has less resistance, but some of it flows down each of the paths. Okay. So anyway, that was a brief digression here. So the main point here is that when you have more resistors in parallel, you end up with less resistance overall. Okay? So let's talk about how you can actually figure out how much resistance you have. So imagine that you have two resistors, and they're connected in parallel, and each one has a resistance of 1,000 ohms. If you took a meter and you measured from the top of that circuit to the bottom, what you would see is you would see a resistance of 500 ohms. So if you have two resistors that are the same value in parallel, the equivalent resistance is half of one of those values. So this would be equivalent to just a single 500 ohm resistor. Okay? If you had 3 resistors in parallel, and each one of them, say, was 900 ohms, that would have an equivalent resistance of 300 ohms. So when all resistors are the same value, the equivalent resistance is 1 resistor divided, so 1 resistor value divided by the number of resistors. So let's say that I had 4 resistors in parallel, and each one was 800 ohms. What would be the equivalent resistance for that circuit?
200?
Yeah, 200 ohms, exactly. All right. So you might ask, well, how common is it to have a circuit where all of the resistors in parallel are the same value? It's actually, it happens fairly regularly. Again, going back to those holiday lights, you can imagine that each one of those bulbs has about the same resistance. You got a bunch of bulbs connected in parallel, you get this situation where you have a bunch of equivalent resistors all connected in parallel. Yeah?
How does tolerance factor into that?
Right. So that's a good question. So we say that these are all 800 ohms, but like you mentioned, there's a tolerance on each resistor. So these would be, say 800 plus or minus 5%. So one of them might be 795 and the other is, 807 and so forth. And so this wouldn't be a perfect calculation, but it would get you in the right ballpark. So you could be more precise, but this would be a kind of a good starting point. Yeah. Other questions?
What happens if the resistance is like different, it's like 600 and 800?
Right. So, yeah. So if they have different values, I'm glad you asked. If they have different values, this formula does not work, and so we need to use a different formula. So let's talk about that. So, when resistors in parallel have different values, use this formula. So the parallel resistance equals 1 divided by 1 over R1 plus 1 over R2 plus 1 over R3 plus, and then you can keep doing that for as many resistors as you have. So that's the formula that you can use if you have different resistor values in parallel. So let's do an example with that. Yeah, you might need a calculator for this one. Yes?
If it's 1 over all of that, wouldn't it just be... Okay, never mind. I'm thinking of algebra right now. I should do
Right, yeah, so, right, it's tempting to look at that and say, well, you got 1 over this. Couldn't you just say that's, R1 plus R2 plus R3? But yeah, and a lot of people get confused and think that's the case, but it turns out that's not actually the way that adding fractions work. So you have to, so I'll show you, we'll go through an example and we'll see how that turns out. So let's say that we have a circuit like this. We've got 5 ohms in parallel with 20 ohms. And we want to find the equivalent resistance. So we want to find that equivalent resistance. Can we use this formula over here where we just look at that and say, well, it's, we divide one of these by how many resistors we have? No, because this formula only applies when all the resistor values are the same. And now we've got different resistor values. So we have to use this formula over here. So we'll call this equivalent resistance, we'll call that REQ for equivalent. So this is equivalent resistance. That equals 1 over 1 over 5 plus 1 over 20. So that is 1 divided by, what's 1 divided by 5? Yep. So 0.2, and then what's 1 divided by 20? 0.05. So that is 1 over, and then we can add 0.2 and 0.05, so we get 0.25. So then we say R equivalent. So what is 1 divided by 0.25? 4. So R equivalent is 4 ohms. So the equivalent resistance here is 4 ohms. In other words, if we took a meter and we hooked one side here and the other side there and we measured the resistance, we would see a resistance of 4 ohms. So what you'll see when you have parallel resistances is that the equivalent resistance is always smaller than the smallest resistance in your circuit. That's because, like I said before with water, basically when you add resistors, you're giving the electricity more paths to follow. So if you just had a single 5 ohm resistor here and then you added another path, you know that it's going to be easier for the electricity to flow than if it just had that 5 ohm path. So the equivalent resistance is always going to be less than the smallest resistor in your circuit. So that's a good way to check your work. When your answer comes out, it better be less than the smallest resistor in your circuit. Otherwise, if it's not, then something is wrong. Okay.
Could you repeat that again?
Yeah. So when you have an equivalent, or when you have a parallel circuit, the equivalent resistance for that circuit will always be less than the smallest resistor in your circuit.
Okay, so our answer would always be less than the lowest value of the resistance.
Exactly. Always less than the smallest resistor. Yeah. And was that the case when we were doing the math this way? Yeah. Remember, we had 800 ohm resistors here, and our equivalent resistance came out to be 200 ohms. So no matter which way you do the calculation, no matter whether the resistors are the same or different, the equivalent resistance in parallel will always be less than the smallest resistor in your circuit. Okay? So, questions about that? All right. So now we've done some calculations with resistors where all the values are the same, and then also we did some values that are different. Do you want to do one more circuit here to practice this different formula?
Yeah, sure.
I do.
All right, cool. Let's do it. All right, so let's say we got a parallel circuit here, and we got 3 resistors this time. And let's see. So all right, so we've got this situation here. So we've got 3 resistors in parallel. 2 of them are 200 ohms, and 1 of them is 25 ohms. So can we use this formula over here, where we just divide by the number of resistors? No, because even though 2 of them are the same, 1 of them is different. So we still have to use that other formula over there. And what is the? We know that our answer had better be less than a certain value. What had our answer better be less than? 25, because that's the smallest resistor in our circuit. So when we do our calculations, we better hope that our answer comes out to be less than 25. Otherwise, we've done something wrong. Okay? So we can use that formula over there, and we say R EQ equals 1 over 1 over 25 plus 1 over 200 plus 1 over 200. So our EQ equals 1 divided by, so what's 1 divided by 25?
0.04.
So 0.04. And then 1 divided by 200? 0.005. And then that again, 0.005. So our equivalent is 1 over, we add those all together, that comes out to be 0.05. So our equivalent, what's 1 divided by 0.05? 20. So the equivalent resistance by our calculations is 20 ohms. Is that less than what we said it should be? Yeah, we said it should be less than 25, came out to be 20. So it passes our check there. So, so that's how we can use that formula. So any questions about that? All right. Cool. So then let's go on and do a little bit of calculator practice, okay? So let's fire up the projector here. Yeah, sure.
Does it matter if you're doing it in decimal or keeping it in fractional form? So like in some of the computer maths, you keep it in fractional form.
You can.
We're going to run into like imaginary numbers later on.
So you can keep this in fractional form, that's fine. We're not going to deal with imaginary numbers in this class.
Okay.
You could, there's lots of different ways to think about electronics. So, so with some AC frequencies and signals, it can be helpful to use imaginary numbers, but we're not going to do that in this class. Did you have a question? No? Okay. Yeah, other questions? Okay, and the other part of your question was, yes, you can keep this in fractional form. You just end up adding fractions. So some people are comfortable with that. You have to find a common denominator. So it would be like 1. So that would be like 4. So sorry, 8 over 200 plus 1 over 200 plus 1 over 200. And then, so that is 1 over 10 over 200. So, and then that becomes 1 over 20. So that just becomes 20. So you can do it with fractions also, but people are just generally less comfortable with that. And when you're dealing with real numbers, generally the fractions don't come out so cleanly. So it's usually better to do it with decimals. Yeah?
In this kind of situation where resistance is different, is the current still the same?
No. So that's a good question. So we said that in series circuits, the current was the same, but the voltage would be different. This is a parallel circuit. So I want to save the voltage and current and Ohm's law for next class, but we will look at parallel circuits with voltage and current and figure out those things. But parallel circuits, there's just kind of a lot to take in, so I want to kind of divide it over 2 classes. Yeah. Yeah, other questions? Okay. Cool. So then let's go on and talk a little bit about calculator practice. All right, so basically the idea is that oftentimes we're dealing with millivolts or kilo ohms or microamps, things like that. So you have these quantities, and they might be big or small, and you want to be able to use them in calculations and use them with Ohm's law and things like that. And so it would be nice to be able to have a quick way to do that in your calculator. So, this assignment in your lab book shows you or gives you a chance to practice with some of those calculations. And the way that we do that is that we use a special feature on our calculators it's on most calculators that allows you to enter exponents. So that's on page 89 in the lab book. And then on the next page, page 91 here, we have a table that just refreshes our memory about what each of these prefixes means. So for instance, we have kilo here, and we see that that's 10 to the power of 3. So what that means is that we remember kilo means 1,000, right? So kilo is 1,000, and that's, but we say that that's 10 to the power of 3. That's what this table is telling us. So how does that actually work? What this power means is it just means you put that many tens next to each other, and then you just put multiplication signs in between. So 10 to the power 3 just means 10 times 10 times 10. That's all that it means. And if you multiply that out on your calculator, you'll see that that equals 1,000 and kilo. So if we say mega, that is 1,000,000. That means 1,000,000. And that also, the table says that that's 10 to the 6th power. So in other words, you put down 6 tens, and then you just multiply them all together. And again, if you did that on the calculator, you would see that if you multiply 10 times 10 times 10 times 10 times 10 times 10, that gives you 1,000,000. Okay, so that's all that's going on with powers. Now we also have some negative powers there. So milli, that's 0.001, or it's 1/1000th. And it's also 10 to the negative 3 power. So when we have a negative power, all that means is you still have the same number of tens. So we still have 3 tens multiplied together, but now we just put 1 divided by that. So 10 to the negative 3 is 1 divided by 10 times 10 times 10. Again, if you did that in the calculator, you would see that that comes out to be 0.001, or 1/1,000. Okay, so we've got all of these prefixes, and this table tells us what they mean, and our calculator allows us to enter these values in a sort of a quick way and do calculations that way without having to type in a whole lot of zeros. So let's look at this book here and try and figure out what the homework is asking us to do. So first of all, it's giving us this value that's 2 microamps, and it's asking what the exponent is for that. So we have to find the exponent for micro. So we come over here to our table, and we see that micro, okay, well that's 10 to the minus 6. So the exponent here, the little number in the upper corner, is minus 6. So we would put down an exponent of minus 6 for that. Can you see that writing on the board? Let me zoom in here a little bit. All right, so we put down we said that the exponent for micro is minus 6, so we write that down. Now, the next thing is that we have a value of 3 kiloohms, so it's asking what the exponent is for that. So we need to find the exponent for kilo. So we come here and we see that for kilo, what is the exponent? 3. Exactly. So we'll write down the exponent for kilo is 3. So now we want to do Ohm's law. We want to imagine that we have a circuit where we have 2 microamps and 3 kiloohm resistor, and we want to find the voltage for that circuit. So we remember with Ohm's law, we can write it down. We've got V, I, and R. We want to find the voltage. We just write down V equals I times R. Okay, so what we want to do to find this voltage is we want to multiply our current I times our resistance R. But we can't just multiply 2 times 3 and say that it's 6 volts, because it's not just 2 amps, it's 2 microamps, and it's not just 3 ohms, it's 3 kiloohms. So what we need to do is we need to use our calculator to help us out here. So many different calculators have this functionality on them. I will show you how to do it on this calculator in particular, but this functionality is present in many different ones, and if you have a different one and you can't quite figure out how to do it, just let me know, or Fred or Stephen, and we can help you work with that. So we're going to turn the calculator on, and what we're going to do is that, first of all, we have to set the mode for our calculator. So up here is the button to change the mode. So if we look at this button here, we see that there's the kind of the normal writing on the button that says DRG, but then above it, there's this blue writing that says Sci or Eng for scientific or engineering. So those are the modes that our calculator can be in. And in order to get to that functionality that has that blue writing on it, we have to push this second button. So we push second, and then we push this button to get into the scientific, or the mode that we're in here. And now you can use these arrows to change between the modes. So we want to be in engineering mode, okay? So we'll set that to engineering mode, then we'll press the enter button down here. And now we're in engineering mode. So that'll give us our answers in these engineering prefixes that we know about. So you know, the answer will come out in one of these prefixes where it's, you know, 10 to the 0, 10 to the third, 10 to the 6th, or minus third, minus 6th, and so on. So Okay. So now we're in the right mode. Now, what we can do is we can do our calculation. So we want to multiply the current times the resistance. So the current here is 2 microamps. So we put in 2, and then for micro, we said that the exponent is -6. So we can do 2, and then there is this functionality that is usually denoted with EE. So if you look at the calculator, there's this little EE above this button here. So, and again, it's in blue, so in order to get to that, I have to push the second and then that EE button. So that's what I'll do. So I'm going to push second EE. So that's a short way of writing times 10 to a certain power. So now I'm going to use this power of -6 here. In order to enter -6, I don't use sort of this subtract button. I actually use this button down here, -6. What's that? 20. Oh, I'm sorry. I hit an extra, I hit a 0 by accident. So I can go back 2, thank you, and then E -6. Okay, so that's sort of a shorthand way of writing 2 micro, 2 times 10 to the -6th. Yeah.
How it looks, that's the great thing.
Yeah, so that's a short way of writing micro. I know it took me, 10 minutes to write that because I'm talking through it, but when you actually get used to it, it goes pretty fast. You just hit 2E -6, and you have that there. And then we want to multiply that by 3 kiloohms because we're doing Ohm's law, right? I times R. So we say times, is there a mouse in here? What? All right, so we say times, now 3 kiloohms. So we would say 3, and then the exponent for kilo is 3. So we would say 3 second E 3. So we've got 2 times 10 to the -6th times 3 to the 3rd, 3 times 10 to the 3rd, and then we hit the equals button on our calculator. We hit equals, and then that gives us our result. And so what we do is we write down the value here. So the value is 6. So up here for value, we would say 6. And then the exponent there is -3. So that's what this is telling us here. 6, and then this is -3. And then the metric result is, what we do is we say that is 6, and then we have to look up what, sorry, -3. We have to look up what -3 means, and we go back to our table, and we see that -3 is milli. So that metric result would be 6 millivolts, because this is Ohm's law. So that's how we would do that. Yeah.
Would it be easier to just add -6 and then add 3 and then -3?
I like the way you're thinking. Yeah. So that's a good way to do it. Yeah. And so that's a great point. So you can, if you look at this, you can see that there's a pattern here. So if you add this exponent, -6, plus the other exponent, 3, you end up with this exponent of -3. So that's, I'm glad that you're thinking about that and you notice that. So you can do that also. and that's a great way of doing the calculations. But if you're using a calculator, you can just write down what the calculator tells you. But it's always better to think about it yourself and get an idea, at least a good approximation of what it should be, and then check and make sure that your calculator is matching your approximation. Yeah, so thank you. So shall we do one more here? All right. So we can look at the next one. This is 6. Well, let's look at this next row down here, okay? So now we've got 2 milliamps. So what was the exponent for milli? So minus 3. And now we've got 3 kiloohms. So if we look at over here, we look at our table and we see that the exponent for kilo is 3. So we can write down an exponent of 3. So now we can do this on our calculator. So we'll write down 2 milliamps. So that would be 2, and then we say second E minus 3, 2 milliamps, and then times 3 E3, and then that gives us a value of 6, and then the exponent is 0 in this case. Like you mentioned, minus 3 plus 3 comes out to 0. So then the metric result, if we look back here at our table, yeah, the prefix for 0 is just units or none. So we don't have to add any prefix there. We can just say 6 volts. Okay? So that's how we do that. So that's what the book is asking you to write out, and that's how you can do it on your calculator. So are there questions about that? Yeah.
I was just going to say, back in prehistoric times,
Uh-huh.
there was a thing called I can't remember the name. It went like this.
Yeah, it
though.
slid
It's called a
around.
slide rule.
Oh, yeah, yeah.
And that's before calculators.
Mm-hmm.
Slide rules would not do exponents, and you had to do the exponents like this for every problem.
Oh, boy. Yeah.
I heard.
Yeah. Uh-huh. So there you go. Okay.
It
So,
also doesn't work very well on a phone calculator, even in the scientific mode.
right. So yet another reason
Get a
to
real calculator.
get a real one.
Walmart and spend $10 and get a calculator.
Yeah. All right, so that's the calculator practice. So please work on that for homework, okay? So then let's go on and do a preview of today's lab. So let's see. Okay, so let's see. I think this is 75. Yeah, Ohm's Law 2. So, yeah. All right, so this is, Ohm's Law 2 on page 75 in the lab book. And then, so this, let's see. So this one, it says we're going to open up circuit 10A. So let's see. We're going to go. So instructor files, and then ET302, and then Ohm's Law 2. All right, so this is circuit 10A, so this is the first part. So in your lab book, this says, using Ohm's law, select the resistor values to obtain the current listed in the table. So we've got 12 volts, and we want to find what resistor we need in order to give us 2 amps. So we want to find the resistance. So again, we can use Ohm's law, V, I, and R. So we want to find the resistor, so we write down R equals, we cover that up, we see that it's V over I. So in this case, for the first one, that'd be 12 volts, and then 2 amps. So that gives us 6 ohms. So we would calculate a resistance of 6 ohms, and we'd come over here and we'd type that in. This is already set to 6 ohms, so we can just leave it. And then we would run this, and then we would check our current value here and make sure that it matches up with what it's supposed to be. So we're measuring a current of 2 amps. And so we would write down the current is 2 amps, and we see that that is in fact what we wanted it to be, so that's good. So we use 6 ohms there and 2 amps. So we're all set, okay? So then you would repeat the process and pick a resistor value that would give you 3 amps, pick a resistor for 4 amps, and so on, all down there, okay? And then same thing down here. You're going to pick resistor values to give you milliamp currents. And then finally over here, you pick resistor values that will give you these microamp values. Now here, this is where we have this note. We have to change the settings on the virtual DMM for this part of the lab. We have to change the settings so that the resistance of the virtual DMM is 1 ohm, okay? So when you come to this part of the lab, you're gonna stop that. You're gonna open up the settings on this multimeter, and you're gonna change the ammeter resistance to 1 ohm. Right now it's set to 1 nano ohm. You just change that to 1 ohm for that part of the circuit only. Okay? For that table in the homework, in the lab. All the rest you leave it the same, but just for that table in the lab you change the setting. Okay? So are there questions there? All right.
If we don't change it, what happens?
So let's see. So if basically you get the wrong values, but I'll show you what happens. So if we leave that at 1 nanoamp, and we wanted to find, we want to have a voltage of 20 volts, and we wanted to have we want to end up with a current of 1 microamp. So again, we would use Ohm's law. We would see that I equals V over R. So we would say that's 20 volts. Or I'm sorry, I'm trying to find the resistance here. So we would say R equals V over I. So that would be 20 volts over 1 microamp. So that comes out to be 20 mega ohms. So if I put in a resistor value here of 20 mega ohms, I type in 20, and then I can use a capital M for mega. So 20 mega ohms. And then I run this, I should see a current of 1 microamp. But let's find out what happens. We get this weird value that's 3.5 microamps. So the computer is having a glitch here. So that's why we need to change the settings. So we need to change this over to 1 ohm. And then if I do that, that gives us about the right value. Okay? So it's just, the computer doesn't make accurate measurements unless you change that setting there. Okay. So, yeah, other questions? All right. All right, so then let's go on to the next. Oh, yeah, question.
Going back to the book real quick, because I came across somewhere.
Yeah.
For the part 2, how do you figure that out?
So, okay, let's take a look. So part 2.
Are we supposed to do the part 2? Correct?
Yeah, you need to do both pages. So, so for the calculator practice, so on the second page, you're still using Ohm's law, but in this case, you're trying to find the current instead of the voltage. So again, you would use Ohm's law, V, I, and R. So in this case, you would just write down I equals V over R. So you would just find your voltage, find your resistance, and then divide the voltage by the resistance to give you the current. Yeah. Okay. So back to the lab here. So,
Try to turn it off the illumination light and see if that helps, because they're having a lot of trouble seeing blue light.
oh, thank you. I apologize for that.
It doesn't show up, and I didn't know if the light being off would help.
Yeah, let me check on that. All right, so the light is off now. Yeah, it's still pretty light, pretty dim. So
Go ahead and turn it on, let's see what it looks like.
that's the light on. That's the light off.
What do you guys think? Can you tell the difference?
Not much. Yeah. So let's see.
That's better.
That's
Now
better.
they can see it.
Yeah. Okay. Thank you. Thank you for telling me. Yeah, I appreciate that because sometimes.
And nobody was seeing anything.
Yeah. Oh, okay. I'm sorry about that. Yeah. Sometimes it's hard for me to tell.
Feedback.
Right. I appreciate that. No, I appreciate that. It's. I'm glad. Otherwise, I wouldn't know.
Is that better for you guys?
Yeah. All right. Thank you. Okay. Yeah. So all right. So so we go through and we do that. For the next part of the lab, we have the voltage and current relationship. So this is, so we'll go back to our folder, and then this is 10B. Yeah, we're on page 76 now. So, so now we're going to fill out this table. So this circuit has two resistors that are in series, and basically it says select the resistor values to obtain the voltages in this table and measure the resulting current using the virtual DMLs. So what's going on here is that we can change, we have two resistors in series, we can change both of those, but we have three different things that are kind of variable, the current and the resistor value. So basically we have one of those things that we can just define one of those to be whatever we want. And then we can use that to calculate the other two. So I like to just set the current to be 1 amp. Okay? So once we set the current to be 1 amp, then we can use Ohm's law to figure out the other values. Okay? So if we have 1 amp and we know that we have a voltage across a resistor of 15 volts, then we can use Ohm's law to figure out what that resistor value should be. So so if we have a resistor, we know that we have 1 amp of current flowing through it, and we have 15 volts across it. We can figure out what that resistance should be. So we use Ohm's law again, V, I, and R. We write down R equals, we cover that up, we see it's V over I. And so that comes out to be 15 volts over 1 amp. So that gives us 15 divided by 1 is just 15 ohms. So we know that this resistor value is 15 ohms. So we can fill in a value for this resistor. We would say that that's 15 ohms. By the same token, over here, if we want to get 5 volts, we could do the same calculations and we would get a resistor value of 5 ohms. So then what we do is we go over to Multisim and we plug in these values and we make sure that our current matches what we think it should be. So we come over here, we've got 20 volts from the power supply. We'll make the first resistor 5 ohms, and then the second resistor 10 ohms. I'm sorry, 15 ohms like we calculated. And then we can check the current up here. So when we run this simulation, we get a current of 1 amp, just like we thought it should be. So we can do that for each of the rows in this table and calculate what our resistors should be and then check our math, make sure that that works out correctly, okay? So I like to pick just a value of 1 amp for all of the currents and then use that to do my calculations. Okay. Any questions about that? All right, and then we're going on to parallel resistors. So so we have a circuit where we have 3 resistors in parallel, and if all of them are 1 kilo ohm, we want to calculate what that resistance should be, and then we'll use Multisim to measure it and check that our measurement matches our calculation. So if we have 3 resistors in parallel and they're all 1,000 ohms, what would be the equivalent resistance there? Yeah, about 333 ohms. We just divide 1,000. Since they're all the same value, we can just divide 1,000 by how many there are. So that would be 1,000 over 3. That would give us about 333 ohms. So we would write down the calculated resistance, 333 ohms. And then we can use Multisim to measure that and check our calculation. So, so we'll come here to the parallel resistors. I'm sorry, I skipped a part here. There, okay. So there's a part where you're doing this with just 2 resistors in parallel, so that would be here. And then we're doing the part where you have 3 in parallel. So we've got 3 resistors in parallel. They're all 1,000 ohms. So we can run the simulation and check our math. And sure enough, it comes out to be about 333 ohms. So you would fill in that whole table there. So down here, you do a very similar thing. You'd calculate the total resistance. You'd measure it. And then this circuit also has it also, so you'd calculate the total resistance, and then you would calculate the current for this circuit. So you would use Ohm's law to calculate the current here, and then you would measure it and see if your measurement checks out and matches your calculation. So that's what you do there. And then that's the end of the lab for today. So are there questions about that? All right, so today's lab is all in multisim. I know normally we do one part in multisim and one part hands-on. Today's lab is all in multisim, but next time we're going to get back to the hands-on stuff. Okay?